Okay, good morning, everyone.
Good
I
morning.
welcome Dr. Pritam Gujarathi sir and I welcome Dr. Patel sir. Today is last day for this STTP and the session is 9 from the Dr. Pritam Gujarathi sir. And Dr. Pritam Gujarathi sir is going to deliver on retrofitted conversion of conventional vehicle into plug-in hybrid vehicle. So I would like to hand over this session to our expert, Dr. Pritam Gujarathi sir. Thank you so much.
Okay, so I will try to share my screen.
Yes, sir.
Is it visible? My voice is clear?
Yes, sir.
Okay, so let us shall we start?
Yes, sir.
Yeah, so today we'll have a short discussion on this conversion of conventional vehicle into plug-in hybrid electric vehicle, retrofitted approach. Yeah, some disturbance is there? Anything?
No, sir. It is okay.
Okay. So let us start with session conversion of conventional vehicle into plug-in hybrid electric vehicle. Retrofitted approach. This is need of an hour as far as country like India is concerned. So developing country is there, lot of population is there, and as we have seen last time that it's very difficult for us because of costing of battery, because of costing of complete EV is very high, and it's very difficult for us to shift from conventional sector directly to electric vehicle sector. It will happen in due time, but if suppose it is possible for us to find some solution which will convert your conventional vehicle into plug-in hybrid electric vehicle, then that will be a better solution. That will be for India. So again, actually, I should start normally with same thing that whenever we think of transportation sector, we think of two things, that is traffic and emission. So hopefully I already told you that a lot of normally everywhere we see webinars and lot of talks are there on this electric vehicle, hybrid electric vehicle. But there are very few people those are thinking that millions of vehicles which are running on the road, and they are conventional IC engine based vehicles, petrol engine, diesel engine is there, and because of that tremendous pollution is there. So what about that vehicles which are running on road? So what is the solution for that vehicle? If suppose if we check predictions of scientists, those who are doing, they are saying that another 10 years or even up to 2035, 40, still IC engine market will be dominating all over the world. Even if you take tremendous care, still if suppose drastic changes are there in policies of all governments, governments of all countries, irrespective of that, another 10 years, IC engine based vehicles will be much more stronger. They will be dominating the road. That's what their prediction is there. So we need to find some solution which will convert normally, or which will have replacement, or whatever vehicles are there, how we can use that vehicles in better way, efficient way, because more than 95% of vehicles which are running on road, they are IC engine based vehicles. So one of the current solution which I told you last time also, and today also I would like to highlight this. I will show you that how is it possible to convert conventional vehicle into plug-in hybrid electric vehicle. How we can go towards this practical oriented approach. I will try to share my experience with you. How I have done one particular thing. I have suggested this because it's not that easy to convert conventional vehicle into plug-in hybrid electric vehicle. So why this is important, as this will contribute towards mitigation of emission problem caused by present vehicles running on road by investigating conversion of conventional vehicle into plug-in hybrid electric vehicle to comply with stringent current and future emission norms. So if we are succeed in doing this particular thing, you will find that tremendous load of electric vehicles which should come on the road, that will reduce and pollution levels will drastically come down. Because what we observe is that when what are 90% of vehicles which are running on road in urban areas, their maximum speed is less than 60 kilometers per hour. So let us have look that how my approach is there and what things I have suggested. So this is the aim for this particular discussion towards sustainable, high efficient, clean and safe transportation. Or we are going towards electric vehicle. It is not possible drastically, so we are doing this particular thing. Now when I started study actually on this particular topic, that I wanted to do some sort of research in electric vehicles or hybrid electric vehicles. So I started searching publications, research publications. So I started standard journals like IEEE, Taylor and Francis, Cambridge, Oxford, Wiley and Sons. What I found is that around 31,239 publications I observed by putting keyword like hybrid electric vehicle, plug-in hybrid electric vehicle. Around 31,239 publications are already available in this area. So I got little tensed actually. So how we can work? Already all work has been done. How is it possible to work in this particular area? Then I started searching gaps. Are there any gaps? Oh, let us work on charger. Charger still publications are more. Let us work on generator part. You can say motor part. So already it is there. Battery ultra capacitor commodity already it is there. Then I found, then when I thought it little bit in, and I was day and night I was in that particular issue to work on hybrid electric vehicle, plug-in hybrid electric vehicle. So then I found that, oh, what about if suppose it is possible for us to convert current vehicle into hybrid electric vehicle, plug-in hybrid electric. Let us see how publication look. And when I checked publication look, I was surprised that only 684 publications I found. That is again not related to retrofitted conversion. That is related to energy management strategy of HEV/PHEV. And only 25 publications I found on conversion of hybrid electric vehicle, plug-in hybrid electric vehicle, retrofitted approach, or related to conversion part. Only 25 publications. I'm talking about standard journals like IEEE, then Wiley and Sons, elsewhere, Taylor and Francis. So I was surprised that, oh, why work was. So I was thinking that why it is not possible when 32,000 publications are available as far as HEV, PHEV is concerned, and why only 25? Why 25? Are people not interested? Why people is not anybody that he in his mind this particular concept came before? Of course, it might have came with many people. So, but still, I thought that what is the problem? So when I thought that what problem it should be, then what I found is that basically there is no space for fitting electric drivetrain. If suppose you check your conventional vehicle, then you will find that where you will fit electric drivetrain. Now what I have electric drivetrain means I need to put motor, I need to put batteries, and I need to put power electronics converter. At least these three things I need. And in addition to this, I need somewhere to control on off, so that some switch or some clutch I can say that for, so that motor will get connected or motor will get disconnected, something like that. Or else motor will continuously run along with engine, and that is not again wise idea. But still, this is what it is. I found it. So why? What is the problem? So this is the main problem. Then I inquired little bit more. I checked that most of the companies are trying, but they still, I don't think that they got any success in proper way, because one more important thing is there which we'll discuss regarding this. So there was less attention, actual research on conversion of conventional vehicle into PHEV in terms of energy management strategy for reduction of. Also, another interesting thing which I observed is that whenever I was thinking on energy management strategy, at that time, most of the publications out of these 32,000 publications, they are on reduction in fuel consumption. But again, there is very less work which is going on reduction in emissions, and which was the most important part here. So there was less work on emission reduction and fuel consumption along with fitting of electric drivetrain. So I started working on this particular part. So when I thought that what is the challenge actually? So it is challenge because of limitation of space for fitting electric drivetrain. Now another thing is that if suppose I ask you, oh, you have electric vehicle, conventional vehicle, you give me your vehicle and I will convert it to electric vehicle. So most of the researchers, most of the knowledgeable person, they said that what is there? We will replace engine with small, you remove that engine, put small engine and put more electric motor, so it will run in proper way, so that it should run efficiently, so that proper things will be there. But practically speaking, that nobody will allow us, that if suppose I say give me your car, I will replace with electric vehicle, I will give you free of cost, I will do conversion, I will take out engine and I will, whatever money we get by selling the engine, we will put it electric drivetrain. You will say sorry, I am not interested in conversion. You should not touch engine part, you should not touch engine part. So the most important part when we check mindset of people is that we need to do all these things with minimum change in mechanical drivetrain component. We don't want to remove anything which like engine, radiator, any device which is there, which is important in driving car. We don't want to remove this, but if it is possible for us to give solution to the public, so that with removing one component or two component, non-important component, some pulley, some drive shaft, some small things, if it is possible, and if it is possible to fit your electric drivetrain or electric powertrain, then that will be the proper solution. Now again, there is a problem that size and weight of battery is very high, so size and weight constraints are there. Now let us say that we have fitted electric drivetrain, whatever it is, in proper way. Now when motor will get operated, when engine will get operated, now how will you play with CAN bus? So inside this there is one CAN bus system is there, by which will take decision of how much fuel should go to engine. So is it possible for us to play with this CAN bus? Are we that much efficient in all that? Means, shall we disturb it or not? Shall we disturb? So what are the practical solutions? How is it possible? So these are the challenges. The another most important challenge is that you need to balance weight when you are doing these things. Or there was one term called center of gravity. So we should not disturb center of gravity. So that is another one most important part. So many of the people tried this, and there were vibrations when it was motor, when your car was running. So why these vibrations was because center of gravity was not properly fixed. That center of gravity point, we need to fix it properly, or there should not be unbalance in weights. So we should, that is another important part. So all these things we need to take into account when you want to convert your conventional vehicle into PHEV. But 100% this will give the solution which is required for us. But it is not at all that much easy task. A lot of people are trying, many companies are trying, but at the same time they didn't got success. There are only 2 companies in India, those who are doing, out of which one company closed. One company still they are claiming that we are succeed, but again still we are not sure that exactly. And all these giants are there, they are also trying at back end, they are not telling, but 100% they are trying to have some product which what I'm thinking is that my approach is a bit different. My approach is that I will have one kit, when I will remove one component and I will put that kit. So that is called as retrofitted approach. So I will not remove anything of machine, only 1 or 2 things I will remove. Even I will not play with CAN bus system and other things for providing basic solutions. So I will remove one or 2 components, mechanical or minimum change in mechanical components, and then I'll fix my electric drivetrain. That is what my aim is actually. So for that purpose, what I have done, I have taken one vehicle. Now this is one rear wheel vehicle where we have fuel tank, IC engine, then there is gearbox, differential, as yesterday we have discussed already, and then this is the wheels of vehicle. So this is your conventional structure of IC engine based car. This is conventional structure of IC engine based car. So I took, actually this is car of one of my friend, Tata Indica diesel car which he has, and we started working on this. So suppose this is 4-cylinder car, 1405 cc, 70 hp, 135 newton meters maximum torque, and as per ARI 19 kilometers per liter, that is average as per ARI. Actually it will give around 14 kilometers per liter on highway, and again as I told you, 8 to 10 kilometers per liter on during your urban areas. Now frontal area, gearbox 43221, I told you, but this is what radius of, these are all specifications which I used for this conversion purpose. Now this is what thing is that. So what was my aim? My aim is to convert this into PHEV. So first important task which was there in my mind is that how it is possible to convert with minimum change in mechanical drivetrain component. That was first to decide strategy, decide architecture actually. How should be your vehicle architecture, that I should be there, so that people will, if suppose you are not removing any important parts, so then people will be ready for conversion, or else people will not ready for conversion. Nobody will, whatever car which is going on in proper way, they are not interested to disturb that particular thing. At the same time, we want that they should run their IC engine car also, and they should run electric vehicle also. If they want, they should able to run both also. So that was the concept here. So what I have done, basically, I have suggested, so sorry, this okay, so this is the proposed simplified architecture. What if suppose you go here, there is one drive shaft here, propeller shaft or drive shaft here, which is connected after gearbox to differential. So it is a long rod, one rod is there. So if it is possible for us to remove this rod, which will go to differential, remove means we'll break this rod in between and we'll connect mechanical device. Only two devices will connect. So what this rod we will remove, we'll remove this propeller shaft, or we also call it as drive shaft, actually that is correct word technically. So we'll remove this drive shaft which is connected between gearbox and drive differential, and then we'll put our system. Our system is what? Motor and electromagnetic clutch. Actually we will not connect motor there, but we'll connect torque coupler there. We'll connect torque coupler. So this is electric motor with torque coupler. So we'll connect torque coupler, and that torque coupler is connected to motor. Torque coupler is connected to motor. So torque coupler is connected to motor, and then for making it on or off, I will connect electromagnetic clutch. So for making it on or off, I am connect electromagnetic clutch. So when this electromagnetic clutch is on, it means this motor is connected. If it is off means actually this motor is connected to differential. When it is on means both are there. IC engine will be there and motor will also be there. So something like that, So now this is what only part is there which I will be introducing in between this drive shaft. So this I will remove this drive shaft and I will put this particular thing. Now this is extra additional part which has been suggested. Means we need power electronics converter, we need battery. So this part will be there, but they are stationary parts. So we can keep this motor, power electronics, power electronics converter and battery. So these parts I will tell you now where we should fix this particular thing which has been suggested. Now this is very basic raw research as far as this conversion of conventional vehicle into PHEV is concerned, which is nothing but by using retrofitted approach. We need more depth in this, but 100% whatever things I am telling you, it will provide solution. If anybody is interested, he can do this in this particular way. There is no doubt in this, but we need to take into consideration other aspects also. It's not that easy, which I am telling you that directly you can go bring battery, do remove this. No, you need to think many aspects, technically, practically, feasibility basis, and so on. But one simple approach which I will tell you, that is possible directly. Now we need to have charger, so we can have charger outside, or you can fix charger here. Now here again, this particular thing, there is another small invention is there here, is instead of using, now if suppose you check conventional structure of PHEV, there is separate converter for motor, there is separate charger, there is separate again DC to DC converter for battery. So here only 7 switch, by using 7, if suppose you know power electronics, then for inverter, 3-phase inverter, we have only 6 switches, power electronic switches. It can be IGBTs or it can be thyristors. So here by 7 switch topology, 7 switch topology is proposed, and by using that, it is possible that 7 switch topology, it will act as converter, it will act as inverter, it will act as DC to DC converter, it will act as buck converter, boost converter. So this particular topology has been suggested. Now what is need of this particular thing? Now another extra thing which has been suggested is that when IC engine is rotating, suppose you are at signal, and when your IC engine is rotating, at that time your auxiliary generator is there, or we can say that alternator rectifier assembly. Alternator rectifier assembly is there, which is used for charging battery and which will help you at the time of starting of engine. So that generator is there, alternator and generator is there. So that rectifier is there. So this rectifier will convert means it will actually charge this auxiliary battery. So if your auxiliary battery is fully charged, IC engine is already coupled to the generator, so the generator is rotating. So this generator, whenever you are at standstill position, it can be used to charge this battery. It can be used to charge this battery. So we need boost converter, which will increase this 12 volt to 196 volt or 220 volt, so that this battery can be charged. Now, most of the things which has been proposed here, which can be used by general persons. General purpose means we can use it for charging with normal 13 ampere, 230 volt. So by that you can charge. So 196 volt, 192 volt batteries are used. So I will tell you one by one. Now these are the possibilities by suggested topology, that this 6 modes are possible. Now first mode is possible that whenever this clutch is open, or you can say that we are not making clutch on, so clutch is off, electromagnetic clutch is off. So through torque coupler you will find that battery, by using battery power electronics converter, and by using motor it is connected to wheels. So we can only your vehicle will run in all electric range. We want to design actually motor ratings, we want to design power electronics rating, we want to design battery rating, how much battery is required, so that your vehicle can run for depending upon your requirement. We'll see that part. So this is how first way. Which second thing is that if suppose you want to rotate, your output requirement is very high and your battery has been discharged, then you can see that engine will run. So this clutch should be on. So clutch should be on. So both engine and motor, both will be there, both are together, will give supply to wheels of vehicle, and both is possible. That is electric assist or hybrid mode. Then IC engine charging. Now this is the third one. This is battery charging. So now here both are giving supply to wheels. Now here it is possible that engine will generate more torque. Less torque is given to, required torque is given to here, and extra torque is used for charging battery through power electronics converter. So this power electronics converter, now it is possible that it will act as a rectifier and it will charge battery. Second thing is that if suppose during regeneration part, so whenever your clutch is open and then your motor kinetic energy of the wheels will be used to charge battery, because motor will rotate, and because of rotation of motor it will produce electricity, and then it is used to charge battery. This is regenerative braking. Then as I told you that during whenever auxiliary battery is completely charged, during that time also by using an engine, for example your vehicle is on and it is done during signal time and auxiliary battery is fully charged, then through this rectifier assembly, alternator rectifier assembly, we can use this power electronics converter, and by using this actually charger is there in between. So this power electronics device along with charger, because that charger itself, or you can use this part also, but this part can be used for converting AC to DC, or if suppose it is only DC, directly you can use same thing for which will act as boost converter and it will charge battery. So these are some of the important parts which we can do by suggested topology. Now here one important thing is that if suppose you are using this particular if you want to that during ideal condition IC engine should charge your main battery, then we need to increase rating of this alternator which is there. So it was 85. I propose double rating. Connected rectifier and topologies, other things it should also work with it. So you need to re-rate actually. Now let us say that suppose I want to, I studied actually that how much is requirement charge once you charge your battery, how much your battery should go. That are things we should decide. So you want to drive your vehicle in city areas, only urban area, then you will find that most of the people also you millions of people, one paper also published actually during how many persons are using how many kilometers they are driving, the kind of driving, other things also. That one particular paper also I presented in Romania. So and then convert this structuring car and so during that particular study, what I observed is that around more than 70% of people who travel for work in city areas, they travel less than 60 kilometer distance. Less than 60 kilometer distance. If time permits, I will show you that data also, basically. So in millions of people are there, those who travel distance less than 60 kilometers, we call it as commutators. So they travels less than 60 kilometers. So I decided to fix range of my battery, so that I should select battery such that my vehicle should run 60 kilometers once you charge. That is range. Range means for one charge your vehicle will run for 60 kilometers. So 60 kilometer is the range for your for our vehicle. That's what first I had decided. Now once you charge, you need to find that how much battery capacity is required, what should be your motor size. So by using very basic calculations, I have done this particular part. So I think these calculations are available. It's not available here because it is very basic calculation. So by using basic fundamental, that at the time of starting, force is equal to mass into acceleration. Again, if suppose you are interested in these calculations, open source paper is available, design, modeling and simulation of conversion of conventional vehicle into PHEV. If suppose you put this in Google, open source paper is available, which was published in Korea actually. So they're very fundamental. So one example is given to you, that if suppose same example which I have, this particular data is from that same paper, that if suppose I want to convert at the time of starting, how much weight of vehicle is there. So if suppose my speed is 0 and I want means at speed of 6 kilometers in 8 seconds or 10 seconds, what is my acceleration? 1.8. That for that acceleration, when the vehicle is driving, initially only very less, rolling resistance of tire. So mu into R, so that particular thing. And then if suppose your vehicle is running with higher speed, then your wind resistance will be there. So this particular thing, so these basic calculations are there. So by using that basic calculations, what I observed is that if I use 22.85 kilowatt hour of motor, then irrespective of you are using 70% of battery capacity. Why 70% of battery capacity? Now this is practical, not ideal condition. Ideal condition, you need around 16 kilowatt hour of motor only, because like how ARI give 19.1, actually it will not be 19.1. So if suppose you give it in ideal way, in standardized way, your battery capacity will be much less. I think so. This is practical oriented thing, that where we can use 70% of battery, we will not allow battery to go down below 30%, and with losses, efficiency, all other things considered, it is 22.85 kilowatt hour. If you fix this amount of battery, then 100% it will give charge of 60 kilometer range. For that purpose, we need to have 15.76 kilowatt hour of motor. Now let us say that this has been designed, this particular thing has been designed. If suppose you want, how you want to calculate this battery rating and motor rating, I will give link of that particular paper if suppose you are interested later on, because very basic calculations are there, everybody will understand in that way. Actually I should put that slide, but I skipped, actually I forget, because I forget, not actually because of staffs are there, because of that, but I later on I realized that it should be there anyway. So this is what now we decided strategy, now we decided battery capacity, we decided motor capacity, we have decided range. Now this particular thing is already decided. Now my main important problem, actually these things, okay, all things are on paper. Actually when you want to do it, where you will fix, where is the components where you can fix this particular thing, where is the space for fitting this electric drivetrain. Now you know that you remove one rod or drive shaft we have removed, and there we want to fix this. So what I have done is that rear end seats are there. Above that seats, we can put your motor, electric motor can be fixed along with power electronics converter, or there is no much more space is required for electronics converter, there we can fix motor. So motor and connections, you can connecting rod is already there. So motor part has been completed there. Now main part is battery. So currently battery has been fixed, and backside boot space which is available for keeping luggage and other things, there we have fixed battery. But still 192 volt and 22.85 kilowatt hour of battery, it was not possible for us to, it was not possible to fix in that particular area. So need to reduce size of battery, and around 15-16 kilowatt hour of battery it is possible to fit. So that we need to check safety part also when you are fixing battery. At that time, connection of battery cables which you are going, that should not have potential difference, which will be because your car outside position is also conducting part. So that particular distance and other, there are specifications for that. So that part also we need to think on. So it was little less, around 15 kilowatt hour of battery is possible on backside, and that particular thing. Now how many batteries are required actually? So another thing was important, that to decide battery voltage. So we have decided battery voltage basically 192 volt, means 12 volt batteries, around 16 batteries of 12 volt, 16 batteries of 12 volt, 198 into 2, yeah, 192 volts. So that is again very critical task to carry this 16 batteries of 12 volt. So normally currently, if suppose you check most of the vehicles, they are using 48 volt as an system. But here advantage is that as your battery voltage will go on increasing, size of cabling will go on reducing. So that is another advantage, and it will be more safe. If suppose your voltage is more, actually it is more safe actually, because large current you are not passing through cable, so heating part of cable will be problematic. But here now, if suppose you are using more number of batteries, then battery management becomes an issue. So battery management part we need to, so yesterday if suppose you might have watched it carefully, thermal hotspots will get created because of temperature. One will get heated, another battery will remain cool. So the battery heated will again it will get overloaded, and that particular battery possible that it will get damaged slowly. And your some of the batteries, means current equalization, voltage equalization among battery series parallel combination becomes a critical issue. So normally if suppose you are using electric vehicles, if suppose people in company they are using, then it has been observed that most of the time they have separate DC to DC converter for equalization of these voltages and proper distribution of current. So that part is there. Now in raw design we have not considered that particular thing, but this is how we can do it practically. So let us say that we have found out solution to this particular thing, and by putting our solution also, since your engine is on front side, if suppose you are fixing battery and motor and back side, and since boot space is given for luggage part where you can keep 200 kg of weight, our weight will be around 190-195 kgs, so around 200 kgs weight will be there. So it may not be a problem as far as disturbance in center of gravity is concerned. So this was one of the solution which we have done for 60 kilometer. Now let us assume that okay, we have fixed battery, we have fixed our electric drivetrain. Now when you will start engine, when you will start motor, this was very critical part actually. This is the critical part, because if suppose you are continuously rotating both, that is not clever idea. But still we want actually, again as I told you, that CAN bus system, how we can play with CAN bus system and other things, microcontroller based all other things are there. So that again, so we wanted that simple solution that anybody can do. But again, if suppose we provide simple solution, people will say that, oh, what work you have done, this is simple, it is known to all of us. So provided, so given little bit mixture of engineering and that particular thing. So first solution which was proposed is that simple thing is that electromagnetic clutch only, operating strategy is only electromagnetic clutch. Make electromagnetic clutch on, don't give any supply to motor, engine will run. When electromagnetic clutch is off, give supply to motor, it will be in electric mode. So it will act as electric vehicle. Give electromagnetic clutch is on, it will act like conventional vehicle. If you give supply to motor and electromagnetic clutch is on, it will act as hybrid electric vehicle. This was the simplest solution which was provided for common people. That if battery is charged fully, then range will be 60 kilometers. Whenever battery is operated, whenever it is charged fully, you can operate 60 kilometers. You can go, you can have run. Will not start IC engine at all during this time. Your electromagnetic clutch is off. So it will be all electric mode with zero emission. Zero emission means tailpipe emission. You are contributing to emissions for charging purpose. If you are charging by renewable energy, no emissions. Now this is the strategy which was simplest strategy. Anybody can do this particular thing who can travel distance less than 60 kilometers. This is one of the way. Another way is rule-based strategy, means by using one centrifugal switch. Now these are practical oriented approaches. If suppose you are going in research, for research this will not work. Why this will not work? The simple things in research, we need complicated things. We need something which we need to show that something extra, something extraordinary we have done, so that your publications will be there. So initially I have done this, all these solutions, everybody told, what is this? This is very simple. What nonsense you are doing. Then I started working on artificial intelligence, and then I put artificial intelligence based solutions for this energy management. And I think 10 to 12 publications I published on artificial intelligence based solutions for energy management. People say, oh, excellent work, excellent work. But practical oriented, you can't do that particular things. It may come. So whatever contribution of that particular things will be there, it may be after 30 years, after 50 years. It may not be now. But so practical oriented solution which you want, it can be in this way. Second way, if suppose simple another approach is that you connect centrifugal switch. Now rule based strategy. What is this rule based strategy? Whenever your vehicle speed, now why this strategy I have suggested, whenever we check engine pattern, emission pattern of engine, I found that if suppose your engine is around 65, not 65, around 85 to 105, then it will have minimum emissions. Actually it will have minimum emissions 60, 70, 72, depending upon its variations are there, but suboptimal zone, maximum zone. So here what we have done is that if suppose your engine is rotating, if suppose your vehicle speed is less than 60 kilometers per hour, then electric vehicle will operate. Whenever vehicle speed requirement is 60 to 120 kilometers per hour, then only IC engine will get operated, and above 120 kilometers per hour, both will get operated. Now why I have suggested this particular thing, because if suppose you are using both hybrid combination together, then okay, fuel consumption, it will be actually more fuel consumption will be there, emissions less, but fuel consumption will be more. But if suppose you want to use this IC engine, we don't have any optimized algorithm actually, so that your engine will operate always at optimum operating points. So this is suboptimum region. So just by experience, by studying the maps, we found that if suppose IC engine is operating during this region, then your both balance, fuel consumption, emission will be balanced. So that particular thing in between 60 to 120 kilometers. So what we have done is that EV will be operated at 60 kilometers per hour using simple centrifugal switch. IC engine can be operated at 60 kilometers per hour. So whenever your speed of propeller shaft goes more than 60 kilometers per hour, automatically centrifugal switch will be on and engine will get connected at 60 kilometers per hour. So engine will get connected at 60 kilometers per hour. Unless and until it comes down of 60 kilometers, that switch will remain on, centrifugal switch will remain on, and it will be connected 60 to 120 kilometers. At 110 kilometers per hour, what we do? We will use sensor and we will give connection, or you can say that your torque coupler or electromagnetic clutch will be on and will give supply to motor. So this is how actually second practical oriented rule based strategy has been proposed. Little complicated. First strategy is easier, anybody can do this. If SOC is another thing, charge of battery, that is state of charge of battery, how much battery charge is available. If it is less than 30%, then it will run with conventional IC engine and it can charge battery. So this can be one of the strategy which can be used for commuters greater than 60 kilometers. Those who have more knowledge regarding electric vehicle and other things, so he can think on this particular strategy. Now, as far as research is concerned, we should go in some depth. So one more strategy I introduced here for you, that is fuzzy logic strategy. So I have used fuzzy logic to decide when engine will operate, when motor will operate, and how we decide this. We decide this depending upon how much charge is there in battery, what is the requirement of speed, what is the requirement of torque, so that my emissions will be less, my fuel consumption will be balanced. So I need to find rules. So if, what is if my torque is high, torque requirement is more, and battery SOC is more, torque requirement is also more, operate both. If my torque requirement is less, battery SOC is high, operate only EV. If and other rules. So I think fuzzy logic things will not go in more technical part here. So fuzzy logic I used so that optimum reduction of emissions and fuel consumption. So around 62 rules has been formed, and then it is decided that engine will get operated, motor will get operated, or both will get operated. Again, you will find 2-3 papers on this fuzzy logic strategies for energy management strategy. So selected driving cycle, urban driving cycle. Now, what is driving cycle? Actually, driving cycle is not correct word. I will show driving pattern. That you start your vehicle, your speed is 0. So you start key. Now your engine is rotating with your vehicle speed is 0. Now your vehicle speed will increase slowly. At 1 second it will be 20, 2 seconds, 5 seconds, 30 km/h. Then it will become 60 km/h. If nobody is there, then you will come down. Suddenly somebody comes in between, your speed will reduce. So at each second, what is speed of vehicle? If suppose you plot that pattern, we call that pattern as driving cycle or driving pattern, or it is normally referred driving cycle. So this is one sample driving cycle, Indian urban driving cycle. If suppose you're driving your vehicle in city like Surat, this can be pattern that you go. Now this is actually around driving vehicle for 2089 seconds. So this much. At each second, what is your speed? It has been only plotted. It has been plotted. Maximum speed I observed in city area is 62.56 km/h. Average speed 23 km/h. Acceleration means change in speed with respect to time is 1.7. Deceleration, suddenly you are putting brake, suddenly your speed is changing from directly 60 to 0, 60 to 20, something like that. It's 2.1 meter per second square. In city areas, when you're driving with only 2000, means only 17 kilometers, if suppose you're driving, you need to stop for 52 times. And your vehicle will remain still because of traffic, 267 seconds. So this was the testing, for testing purpose, this particular sample driving cycle is used. So what we observed is that if suppose you're using conventional vehicles, Tata Indica diesel, this particular test carried out on Tata, and all parameters we used is Tata Indica diesel vehicle. In this diesel vehicle, you get mileage in city 11.36 kilometers per liter. In city area, 11.36 kilometers per liter, where NOx emissions are 0.6 grams per kilometer and PM emissions are 0.0417 grams per kilometer or 41 milligrams per kilometer. So if you use simple strategy, on-off strategies, for distance less than 60 kilometers, there is no consumption, 0 emission. Simple on-off strategy. This electromagnetic clutch is off, you run your electric vehicle unless and until it is discharged. No emissions. No emissions, 0 emissions if you charge by renewable sources. You are shifting your emissions from populated area to unpopulated area. So whatever emissions are there for generation, that will be there. Simple rule-based strategy, as I told you, that less than 60 km/h vehicle speed is there, electric motor will operate. 60 to 120, IC engine will operate. Above 120, both will operate. So distance greater than 60 kilometers, we can use this. Now this all things has been tested for 100 kilometers so that we can compare. So your vehicle is run for 100 kilometers. If your distance is greater than 60 kilometers, and if suppose your battery is fully charged, state of charge is 1, then your mileage will increase around 27.38 kilometers per liter. your NOx will reduce, also your PM will reduce. But this reduction in NOx, it does not comply with your current emission norms. It should be 0.5, less than 0.5 NOx for BS4 norms. BS4. Now I am not talking about BS6 norms. BS4 norms, it should be less than 0.5 for this. I think this is 0.1, less than 0.1. It should be 0.01. It means. So it does not comply with actually norms. Then this is if suppose your battery is only 70% charged, then your mileage will be less, your NOx will be more, and this PM is at comparable level. So this is what it has been observed. If we use fuzzy logic strategy, and if you start at 70%, then you will find that in between results you will get in between these two, that is around 0.37 grams. It will comply with NOx and PM norms, and again this mileage will also be better. So it will comply with BS3 or BS4 norms, I think. BS4 norms. So yeah, it is norms are here actually, sorry. BS3 norms, BS4 not possible, BS3 norms, here it is, yeah. So this BS3 norms, it is comply with BS3 norms. So these are the norms actually. 0.5, so it is less than 0.5, it is more than 0.5, more than 0.5, more than 0.5. So only fuzzy logic strategy will comply as far as NOx is concerned, as far as BS3 norms. BS4 not possible by using this. It needs complicated control strategy and other things. So this was applicable from 2010 and this particular thing. So PM, I think 0.0025, so not possible. Here it is possible. So fuzzy logic not possible, PM also norms, but one is possible, another is not possible for PM norms. So this is how actually we can do, but still it's quite better. Tremendous emissions can be reduced if suppose we can do this particular thing. So these are the summary of results. These are the results which are plotted second by second. If suppose you're driving your vehicle for 100 kilometers, so your 15,371 seconds are required. If suppose so, these conventional vehicles, if suppose you check your fuel consumption in grams per second, it is given around 60 grams per second. It will go up to 30-40 is common, and here it is only 9 grams per second. So this plot, so this part has been again reduced drastically. Fuel consumption, your 3 grams per second, and up to 60 kilometers means around 6,000 to 7,000 seconds. It's approximate I'm talking, because I don't know exactly what time. There is no emissions. There are no emissions actually. There are no emissions here. Because it is working initially in, this is working initially is in EV mode only, electric mode. So electric mode. So this is PM again 0.004 here, 6 into 10 to the power minus 3. So 0.0006 0004. So drastic reduction is possible in PM as well as fuel consumption. NOx, actually NOx also you will find that grams per second, this 1.5 grams per second, here 20.25 grams per second. So again it is reduction is there, and same thing. Your battery 0.70% charging, it is coming down. It takes 60 kilometers. For first 60 kilometers your battery will discharge. Actually this is not only discharge, it's charge discharge is there in small way. And then your battery, we are not operating battery when your battery goes below 30%. So at 30% you are not operating battery. So this is how. Then these are additional results like engine efficiency, driving cycle, again same driving cycle, engine efficiency. Engine is not operating initial part, and it will be around maximum efficiency is 0.32 or something like that. And then these are the other efficiencies, because your efficiency of engine, it is your engine is operating at 15% also, because we need to balance all things, fuel consumption, efficiency. Motor efficiency along with converter, it has been considered, and it is maximum efficiency is around 0.8%, 882%. So minus when it indicates, it means regeneration. Whenever there is regeneration, it will be minus. So that particular part is there. Battery voltage 205, it will drop down, it will increase, decrease, and this is what it is. Around 400 ampere current at 192 kilovolt it is taking. So if suppose you are operating at less voltage, again your current will be very high. So packaging of battery, your cables requirements will cause tremendous heat and management of that heat is another problem. If suppose, so that is again a critical issue whenever you are using higher rating, higher capacity of batteries. The more kilowatt hour of battery you are using, there will be problematic as far as your current is concerned. Now here also it is going up to, so cable size will be very high, because 400 ampere current they should withstand. So that is another thing. So this is what it is. Conversion of conventional vehicle is promising solution. So what we observe is that around 57% of saving in fuel consumption, 12% and 57% of NOx reduction possible with fully charged batteries. Now you will say that, oh yes, okay, you told how to do conversion. What about cost? Suppose I want to convert my vehicle into plug-in hybrid electric vehicle. What is costing part? Please let me know regarding costing things. So if suppose we check costing trends, what we observe is, again you will find one publication that costing conversion of conventional vehicle into plug-in electric vehicle costing part, only that part. It is again open source publication. So 55% of battery costing is there in your EV costing. If suppose you take electric powertrain costing, you find that total costing, 55% of costing is there of battery, 18% motor, 24% converter inverter, and controller 3%. If suppose you check battery technology, there are two types of technology currently we are using in battery. First technology is lithium technology. Second technology is NIMH, nickel metal hydride technology. Very popular technologies. 70% of people prefer, 70% of manufacturing companies, electric vehicle manufacturing companies, they prefer this lithium ion technology. In lithium ion technology, these are the variations which are available. Now, if suppose you check, these are parameters. This is first, second, third, fourth. So this is 4 is better. When you come towards center, it is not good as far as that particular. For example, now here 1, 2, 3, and 4 specific energy. So lithium, nickel, cobalt, aluminum battery, NCA battery has very excellent specific energy characteristics. Means specific energy means for long time you can use it better. Specific power is also excellent. But here, whenever this battery is concerned, safety is only 50%. If suppose this is 100%, safety is only 50%. Whenever your vehicle has impact, whenever using lithium technology, whenever your vehicle have accident, whenever your vehicle have impact, it will catch fire. It will catch fire. Lot of cases has been observed of this particular thing. So they are working on packaging technology. So if suppose you are using packaging properly, then this particular thing can be there. So performance, 75% performance. Lifespan is very good. Cost is very high. So here second only 2. So cost is very high, double cost approximately. Very high costing will be there. Now if suppose you check here, specific energy is less, cost is tremendously high, lithium titanite. Then here LMO battery, that is magnesium oxide. Then this lithium magnesium oxide. So here again, so this, if suppose you check all comparison, you'll find that lithium iron phosphate battery and NMC battery, these two are better. These two are better in all aspects. So a lot of research is going on in this particular thing. So enter technology is there of lithium in this particular slide. Currently a lot of research is going on, and basically the same company from where I took this slide, which is BCG, which is company, BCG company is actually highest selling battery company in US. So this company, they are telling that we are in process, or we are about to complete research on lithium technology, or we call it as lithium air battery, which will go around 5 times more than with same size and same weight compared that of conventional lead acid lithium ion batteries. Around, if suppose 150 or 180 kilometers is there, it will go around 700 kilometers. So around 5 times, 150 and 750, around like that. So around 4 to 5 times lithium ion battery compared to conventional same battery size and weight. So this is how they are claiming. Other technologies currently on which research is going on, they are actually lead dioxide batteries, PbO2. nickel cadmium already is there. We are not actually. This is another thing which nowadays zebra battery, that is sodium nickel chloride, NiCl, NaNiCl batteries. So a lot of papers we are observing currently, and it is saying, people are saying, those who are working in battery technology. I'm not working actually in battery technology, but they are telling that this can be one of the futuristic batteries, because this field battery will not catch fire, cost is very less. Other parts are sodium chloride and other things. There is no problem in raw material and other things. So this can be a futuristic battery, NaNiCl battery. Then sodium sulfur. So these are some of the technologies which low temperature, high temperature technologies, which are normally observed in research papers, or you will find that as far as electric vehicle research is concerned. Same thing which is there. Now this energy density is related to range, power density is related to pickup, so, or acceleration. So you will find that this is the condition of all batteries, nickel cadmium, nickel metal hydride, zebra batteries, and this is the requirement as far as acceleration is concerned, as full HEV, PHEV. So where NIMH is there and nickel cadmium is there, we are not using lead acid battery. Very high power lithium ion battery. This is all actually currently in research stage, or very high capacity is required. And this is a battery electric vehicle, because you need more range also, and power density is okay. So this is how power density is related to acceleration part. So this is the here actually one important part is that currently also a lot of papers are available on super capacitor, ultra capacitors. So this ultra capacitors energy density is very less, power density is very high. So in combinations are proposed by many researchers, so that also we can consider as. Now we'll say that how much is costing actually of battery. So it was around 10 years back 80,000 rupees per kilowatt hour. It has came down to around 18,000 rupees per kilowatt hour currently. So in 2020 it was forecasted to around 20,000 rupees per kilowatt hour, and it should come down around 10,000 in coming few years. If suppose you check power electronics costing, converter costing, around 25 costing are for power electronics devices like thyristors, IGBTs, which we are using, 25% for PCB, and so on. You will talk about motors. You will find that irrespective of induction motor is very popular. 83% of electric motors which are using are, you can say that in propulsion systems, they are synchronous motors, and only 13% of motors are induction motors. A lot of research is going on in reluctance motor. If suppose you check costing part, what we observe is around it. Costing of motors is different. If suppose you produce 100 motors, and if you produce 1,000 motors, costing of 1,000 motors will be more. So batch production of motors will be, here it is given, 3,000 rupees per kilowatt hour for 10,000, 2,800 rupees per kilowatt for 1 lakh, and 2,640 rupees per kilowatt for 10 lakh. So if suppose you put batch production, then your costing will be much more. So what our targeted cost for 960 rupees per kilowatt hour we have achieved in 2016. And we are looking towards cost of 640 rupees per kilowatt hour, and hopefully we will achieve in 2020 only. That target was there. So cost analysis has been done for again same parameter machines which we have converted, same particular thing we used. And how much is initial investment which you require if suppose you want to convert this conventional vehicle into PHEV? So initial investment is well around 2 lakh rupees for standard components. And so this particular thing, all these things I'm talking, if suppose I buy all my components of qualitative based from US, Europe, this all costing is of that particular thing. If we use local labor, Chinese, Korean, this costing will come down. So if suppose whatever costing which I designed for 22.5 kilowatt hour, it is normal actual costing, around 3,74,000 rupees required for conversion purpose, with including labor, everything. and 2,29,000 rupees required with standard. Standard means battery capacity is not 22 kilowatt but 15.76 kilowatt hour. By permanent magnet machines, induction machines, same costing, little difference is there. Now, if suppose I consider that my traveling is 60 kilometers per day, then how will be the payback if suppose I use international components? Around 2 lakhs. And if suppose I use local components, if I travel every day 60 kilometers, then within 2.8 years my payback will be there. 2.8 years my payback will be there. And if suppose I use local components, then around 1.38 years my payback will be there. Whatever money I'm investing, that money I will get it back through fuel consumption reduction, and I have considered electricity cost also, everything considered, and by that around within 1.38 years I will get my money which I have invested after conversion. This for synchronous machine, this for induction machine. Synchronous machine is a little bit costlier compared to induction machine, and because of that I think costing is little more. This is the rate of return on investment, ROI, that is around 50% per year I get, 72% per year if suppose I use local market. So this is about to end of presentation, that future work and direction. Real-time retrofitted conversion is challenging task, but at the same time we should think like Tesla, that nobody have done, we should try to do it. Everything is known to everybody, but we are not doing it. That is main problem. We should do it. That is the if you do it, you 100% there will be challenges. It's not that easy task, but you will find solution if suppose you put wholeheartedly in that part. So here simplified one component mechanical change conversion is proposed, and implementation of again energy management strategy is critical task. That is what it is observed. So we need that instead of using complex EMS, computational complexity and programming, with available CAN bus, it is not possible for us. We need another device like DSP. If suppose you want to use proper energy management strategy, that check battery capacity, how much charge of battery is there, what is requirement. If suppose I want to use fuzzy logic strategy, or I want to use any strategy which will use automatic things will be happen when you put in hybrid mode, automatically it will decide, or we call it as energy management strategy, we need another device like DSP. But again, we need to have a low cost real-time implementation of EMS in coordination with CAN bus controller. So we need to go peep inside this CAN network, and that is again critical task. So that is another research which you can have. Simple solution. Again, it is possible, simplified. Low cost microcontroller, by using low cost microcontroller, so this is possible. But again, we need to have some sort of basic understanding of how CAN bus operates, so that particular thing. So reduction in size of weight of electric powertrain is another area where we should concentrate, or we can concentrate. Already same thing I already told you yesterday. So some of the references are there here, which has been used a lot of double, I think, one slide. So this is how it is. If suppose you are interested in any problematic, anything are there, you can contact me on this email ID. So if possible, I may help you if possible. If suppose my area of research is there, or if suppose anything is there, I may, whatever possible I can. So this is what it is. Thank you very much. Thanks a lot for listening.
Thank you so much, sir. And some questions from the participants.
Yeah, so I will stop sharing screen.
Yes, sir.
Yeah.
Yes, sir. It is on screen. This question
Yeah.
from Niro.
What are the strategies used for finding optimum region to reduce fuel consumption and emission? Sir, there are many methods are there actually. Normally, what we say, we use optimization for this. And in optimization, classical optimization techniques are there, like dynamic programming, linear programming, non-linear programming, or artificial intelligence based strategies are there, which are nothing that we call as computational intelligence based strategies, which is now you will find, if suppose you put research, if you put converted vehicles, around 6 to 8 papers you will find on my name, like gray wolf algorithm I used, that how gray wolf they try to uh, find the prey, or how they will find their food. How they do that, that particular things have been modeled in mathematics and it has been used. Or how bee colonies gather food for their survival, bee colonies, artificial bee colonies. So artificial bee colony algorithm is there, ant algorithms are there. So many artificial intelligence based methods are there, which can be used to find optimum region to reduce fuel consumption emission. Actually, we need multi-objective optimization here. Single objective optimization is not possible, because if one emission is increased at one specific point, another will decrease. You have hydrocarbons, CO, carbon monoxide, PM, and then you have another thing called as NOx. So if suppose you try to balance along with fuel consumption, it is not possible. So we need to have some compromisation, and so multi-objective optimization techniques are required. That is also one of the area currently people are looking. Most of the work has been done for reduction in only emissions or only fuel consumption. Combined emissions and fuel consumption, rare papers are, very few papers are available. But we need to use AI based or computational intelligence based methods, or it is also called as evolutionary computational methods. So evolutionary computational methods are currently used. There is advantage of that particular method, that we can use these methods for real-time implementation. So that is one of the advantage of these methods. I think I hope I have given answer to your question.
Thank you so much, sir. And one more question, sir.
What is impact of SOC of battery if vehicle have to run on upward and downward area continuously? Now, the first important part we should understand is that if suppose you are using battery, this battery actually is not a source actually for vehicle. If suppose you go in more depth, then what we found is that battery is actually not, because vehicle you need continuous fluctuating current is required, or pulse current is required for vehicle. And if suppose you are drawing pulse current from the battery, then battery you will find that its chemical structure mechanical, because of vibration or other things, these electrodes which are there inside the battery, it will have effect on its lifetime. So life cycle of battery will get reduced drastically if suppose you continuously draw fluctuating current. So if suppose you are going on upward area, then 100% battery current drawn will be very high. Battery current drawn will be very high. So it will 100% affect your battery lifetime. What it means actually, battery life is not in terms of years, but it is in terms of charging, discharging, and hence it will 100% affect that particular thing. Nowadays they are working more on SOC of battery, means battery lifetime and other things. So currently whatever batteries are available, they are capable of taking this pulse current. They are capable of taking, because you are charging and discharging also basically by using this pulse current. So that is possible actually. Now when you are going in downward direction, again same problem is there. When you are going in downward direction, suppose during that time, what will happen? For small amount of time, large kinetic energy is available. So if suppose you switch off your vehicle and you are going in downward direction, tremendous amount of kinetic energy which is available, you by using generator you are converting it to electrical energy. It may not possible for your battery to take all that energy, because battery cannot take that large amount of energy for a shorter amount of time. So again there will be problem for battery life here. So what we do normally, we use mechanical braking in addition to regenerative braking, so that we can charge battery up to its optimum capacity, so that its life will not disturb, and remaining energy we waste in mechanical braking. So we use it in combination. I hope again I have given answer to your question. Impact of SOC of battery when going in upward and downward direction.
Yes, sir. One more question, sir.
100% plug-in hybrid recharge while driving. 100% it will recharge while driving. It will recharge. 100% it will recharge while driving. Yes, yes, yes.
Okay, sir.
It will recharge while driving. Now, actually, if suppose you will be surprised to know that your Indian urban driving cycle has highest regenerative energy available compared to world. I have studied all worldwide driving cycles, and Indian driving cycle have highest regenerative energy which is available. But again, as I told you, that it is not possible for us to capture 100% of regenerative energy. Yesterday I told you that around 25 to 30% of regenerative energy we can capture, and 70% again still we are wasting. So that is another area of research. 100% is possible to charge your battery by using PHEV. 100% possible.
Okay, sir. No more questions from the participants.
Yeah. So I hope that session is useful to all of you. And
yes, sir. Exactly. Actually, we also receive many reviews that they find something new for the research from the session. So I hope so it will be really good for all our participation. So once again, sir, thank you very much for deliver such a wonderful speech and provide such a wonderful guideline to our faculty members as well as students for the research as well as teaching purpose. So dear participation, today is the last day and it is the last session of our 5-day which co-sponsor STTP on the new scope of research in electrical engineering. In this STTP, the total 9 expert speakers we have invited from the different areas, and I hope so it will be really helpful to you. If we take a small review, then the first session was delivered by Dr. Nikunj Patel on the role of electric motors in advancement of electric vehicle. Second session was delivered by Dr. Mohan Kole from the Norway. He has delivered on the role of informations, communications and technologies infrastructures for the promoting of sustainable technologies, and also discuss about some case study on the smart home energy. The third session was delivered by Dr. Jitendraji Jamnani from the Pandit Dindayal Petroleum University. He has discussed on the power qualities, issues, mitigations and some standards. Then after, the fourth session was delivered by Dr. Ritesh Patel from the GSET. He has delivered on electrical characterizations of the nano dielectrics for the power industries. The fifth session was delivered by Dr. P. Kundu from the Sardar Vallabhbhai National Institute of Technology. He has delivered on condition monitoring of transformer. The sixth session was delivered by Dr. Sobaraj Arya sir from the Sardar Vallabhbhai University. He has delivered on custom power devices and its applications. Then seven session was conducted by Varsha Shah, and Dr. Varsha Shah has delivered on scope of research in electrical vehicles. The eighth session was delivered by 8 and 9. Both session delivered by our present guest, Dr. Pritam Keshavdas Gujarathi sir from the Oman. And I am thankful to all the speakers for accept our participation and deliver such a wonderful talk. I am also thankful at the end of this session. I like to offer my thanks to all participation and the many people. So I say that first I thankful to the Professor Kausik Dhola sir as the joint coordinator of this event. I am thankful to Dr. Professor Krunal Chaudhary for handle online activities as well as online issues and media activities. I am thankful to our principal, Sir Dr. Jignesh Vagasya, for continuously support us to make this event success. I am thankful to our trustee members. They are not able to join this because of some issues, and they are busy with some other tasks. So I am also thankful to those for continuously encourage us to conduct such kind of event in our institute. My biggest thankful to the Guj Coast because without them funding, this event will not possible to conduct. And I am also thankful to our participants to make this event success. Last but not least, I am thankful to all those people who are directly or indirectly support us or make success this event. So thank you very much all. And with this, I just close this event today. So bye, see you, and take care.
Thank you so
Sir,
much,
thank
sir.
you very much.
Thanks a lot.